Hi, my name is LaRocca, and I am in my fourth year as a PhD student in the Department of Geography and Environmental Engineering at Johns Hopkins University. Today I will be discussing a project which aims to broaden the discourse on infrastructure interdependence by modeling the ecology of infrastructure systems. I was assisted in this work by my research advisor, Dr. Seth Geikema, as well as by Julia Cole, a master's student at Johns Hopkins, and Dr. Eric Sanderson, a biologist at the Wildlife Conservation Society in New York. Infrastructure systems play a key role in many aspects of our daily lives. Such systems include electric power transmission and distribution, drinking water, wastewater, the internet, transportation, and cellular communication. Unfortunately, infrastructure systems are prone to failures as a result of hazards, including natural hazards such as hurricanes, earthquakes, and tsunamis, and man-made hazards such as terrorism and accidents. Many infrastructure systems are interdependent. That is, the functionality of one system is related to the functionality of another. In 2004, Rinaldi described 4 types of interdependencies: physical, geographical, cyber, and logical. Infrastructure systems are complex, contain dependencies and interdependencies, and often span a large geographical scale. These factors make it difficult to model the reliability of such systems. Current modeling approaches include simulation, optimization, decision analysis, input-output analysis, and network theory. In this talk, I will introduce a new approach that is based on ideas that originated in ecological network modeling. Ecological networks share many similarities with infrastructure networks. They are large-scale, involve complex interactions among many subnetworks, and exhibit failures in the face of external loading events. Traditional approaches for modeling ecological networks rely on the concept of food webs. A food web assumes that food is the limiting factor in the growth of a population, ignoring the many non-food factors that are known to influence the presence, size, and spatial extent of a population. Mirror webs were proposed as a way of incorporating the dependence of populations on environmental factors into typical predator-prey food webs. They include factors such as topography, water, wetlands, soil types, wind, and rainfall. These factors are then represented in the form of a graph. The nodes are the species, such as a beaver shown here, and the influencing factors, such as appropriate trees and a slowly meandering stream. The edges in the graph represent dependencies. In this work, I propose applying the concept of a mirror web to infrastructure systems. With this approach, we can examine multiple infrastructure systems and include all elements of the system and their dependencies. For example, a pump in a water distribution system requires a stable foundation, an operator, water input, a pipe connection for output, and maintenance. In turn, a stable foundation is dependent on construction standards as well as soil type and soil moisture. And the pump also requires power in order to operate, and is therefore connected to the electric power system. To demonstrate the application of the mirror web approach to infrastructure systems, I developed a fictitious system including water distribution, power distribution, and transportation. The networks for each of these consist of elements commonly present in such systems. The water system is comprised of a lake, treatment plant, tank, chlorine booster, valve, pump, and pipes. The power system contains a generation station, substation, switch, lines, and poles, and the transportation system includes roads. The performance of each element is dependent on other elements in the system as well as additional factors such as soil type, presence of operators, and maintenance. I developed a full mirror web for the infrastructure systems shown in the previous slide, consisting of the water, power, and transportation systems. Dependencies between system elements are represented by arrows pointing from a given system element to an element which depends on it. For example, an arrow points from line to treatment plant because the treatment plant requires power lines to supply electricity. The dashed lines here represent elements not explicitly considered in our case study. For our case study, we assigned each network element or element component, for example, the tank foundation, a fragility curve describing the probability of failure as a function of wind speed. For some network elements, such as tank foundation, shown here, the fragility curve was dependent on additional factors associated with that element, such as soil type. The fragility curves used in this simulation are for illustrative purposes only. While an attempt was made at realism, they are based on expert judgment rather than real data. We simulated two hurricane events, a 75-mile-per-hour storm and a 110-mile-per-hour storm. For a given storm, we assigned each network element a failure state, with probability from the associated fragility curve. If a network element relied on more than one component for operation, such as pole foundation and pole material, the element was designated as failed if one or more of its components failed. After the failure state of each network element was initially calculated, failures were propagated through the network based on dependency matrices created from the mirror web. For instance, if the road leading to the treatment plant failed, the treatment plant would also fail because it relies on operators and chemicals, which both require transportation to get to the plant. Here is an example simulation showing initial failure states. As you can see, in the water distribution system, the pump and one pipe have failed. In the power system, there are 3 pole failures and 1 line failure, and 1 road has failed. We then propagate the failures throughout the systems. We start with the water system. Because a pipe has failed, everything else downstream will no longer be connected to the source and will therefore also fail. And because the power line connected to the treatment plant has failed, the treatment plant also fails, along with everything downstream from it. Now, we propagate failures throughout the power system. We then check to see if any currently failed elements will cause additional failures as a result of dependencies. In this case, our failure propagation has reached a steady state. We see that all 3 residences have lost water. Residence 1 has also lost power, while residences 2 and 3 remain connected to the power source. Now, let's assume that road 3 also fails. Then, operators will be cut off from accessing the generation station. So, the entire power system will fail and all residences will lose power. We conducted 100,000 simulations for each storm. For each simulation, we recorded the final status of each residence with regard to connection to water, power, and transportation. To provide a comparison with the approach using dependencies from the mirror web, we also considered a case in which the water, power, and transportation systems are not dependent on each other. That is, the water system is not dependent on the state of the power or transportation systems, and the power system is not dependent on the transportation system. Using the initial failure states of individual network elements from before, we propagated failures through the system based only on intra-system dependencies. For example, a pump depending on a pipe, rather than inter-system dependencies. For example, a pump depending on an electric line. Our simulation results are quantified as probabilities that power, water, or transportation will fail at each of the residences in our system when subjected to a hurricane. As the table above shows, using our mirror web approach to include inter-system dependencies results in higher failure probability estimates for both power and water than an approach that ignores these dependencies. The roads are not dependent on either power or water, so the transportation failure probabilities are the same for the 2 approaches. We see that with the mirror web approach, water has a higher probability of failure at all 3 residences than power or transportation. This is likely related to the fact that the water system is dependent on both the power and transportation systems. Mirror webs provide a convenient model construct for expanding the factors considered in modeling the performance and reliability of interdependent infrastructure systems by allowing us to consider additional factors independent of the hazard load and management factors. The increased flexibility and accuracy in the representation of the mirror web does come at a cost. Significantly more information is needed and computational time may be extended. However, we feel that the mirror web's approach offers a significant advantage over existing approaches and provides the basis for a more realistic representation and estimation of the performance and reliability of interdependent infrastructure systems. Thank you for listening. This concludes my talk.